All right, we're going to work through some quick problems here that ask us to sort of think about entropy, enthalpy, Gibbs free energy change, and how that relates to thermodynamic favorability of a given reaction. But we're going to start first with entropy and just looking at a couple of substances, comparing the two, and trying to understand which of the two substances has a greater or higher positional entropy, or more disorder, if you will. As you look at the first example, you've got hydrochloric acid in an aqueous state or hydrogen chloride gas. Which of these two is going to have greater entropy or more disorder? Gases always will be more disordered than your liquids, your aqueous phases, or your solids. So gases, more entropy here. As you look at the second example, we're comparing solid water to liquid water. Again, between the two phases, the liquid phase will have a greater amount of disorder or disorganization than the solid phase will. As you look at part C here, it says argon gas at 5 atmospheres or argon gas at 0.3 atmospheres. In this example, the gases under less pressure will exhibit a greater entropy or more disorder. Again, as you think about this, putting a gas under a greater pressure is going to force those molecules into a more ordered state. And so a less pressure or larger volume is going to allow them to be more disorganized, more crazy at that lower pressure. Part D, we've got a solid and we've got a gas. This one, the gas is going to be more disordered than the solid will. Additionally, it's a just more complex molecule, so we would anticipate a greater amount of disorder in the P4O10 versus just the solid P4. In the last example here, we've got NO2, we've got N2O4, both gases. So both pretty disordered states. How are we going to choose here? It comes down to the complexity of the molecule. The N2O4 is more complex. There are more electrons there, which will therefore allow for a greater amount of entropy or disorder as opposed to the NO2. You'll also have to apply this idea of entropy to changes and looking at chemical reactions and identifying what's going on with the entropy change, just sort of qualitatively. As I look at the first reaction that's provided to me here, I see that I go from 2 aqueous ions to a solid precipitate, if you will, or the solid state. Here, that implies that my entropy change is negative. In other words, we're forming something that is more ordered. And again, a negative entropy change, more ordered, less chaos. We go from aqueous to solid. Conversely, as you look at part B here, we've got a solid that forms gas molecules. So here our entropy change is going to be positive. We're forming more disorder, more chaos. And then lastly, part C here, we're given 2 moles of gases on the left and 2 moles of gases on the right. And so as we try and think about what's going on with our change in entropy here, change in entropy cannot be determined. Because we have the same number of gaseous molecules on the left as we do gaseous molecules on the right, or moles of each of those on the left and as on the right. So we can't really tell in this case. We're both in the same state. On both sides of the equation, we've got the same number of moles of each of those gases. Problem number 3, we start some of our quantitative analysis. So as you look at this first one, we're asked to calculate the entropy change for the following reaction using the data provided. As you look at this one, you try to sort of qualitatively do it. It's a little bit tricky to do because we've got solid state forming solid state. So it's going to be a little difficult to do sort of just qualitatively, much like in that last example, part C. So in this particular example, though, we are given entropy values for each of the things in the equation. And so to solve this, you can use your formula chart. The entropy change can be determined from the sum of the entropy changes of your products minus the sum of your entropy changes of your reactants. And you'll be provided with these values in your problems as you're working, so it's simply a matter of plugging them into the formula and solving. As you put this together, the products, the sum of your entropy changes for your products will be 2 moles times the entropy change there for iron, which is going to be 27 joules per mole Kelvin, plus, again, the sum of 1 time the entropy change, or 1 mole, times the entropy change for our aluminum oxide, which will be 51 joules per mole Kelvin. That'll be the sum of the entropy changes for our products. We'll subtract from that the sum of the entropy changes for our reactants. In this case, it's going to be 1 mole of our iron oxide there, which we have provided to us is given 90 joules per mole Kelvin, plus 2 moles times our 28 joules per mole Kelvin. Close it off there. And then it's just a matter of plugging this into your calculator and solving. You should get then an entropy change for this reaction to be negative 41 joules per Kelvin. And again, as you think about, does this answer sort of make sense? It does. We shouldn't anticipate a huge change in entropy because we've got solid state, solid state, solid state, solid state, and again, the number of moles stay the same on each side. So that makes sense in terms of the overall entropy change for this reaction. All right, as you look at number 4, another type of thermodynamics problem that you're going to have to solve here. This time we're asked to calculate delta G for the following reaction using the data provided. But the Gibbs free energy change can be calculated by summing together the Gibbs free energy changes for your products and subtracting from that the sum of the Gibbs free energy changes of your reactants. So this, again, is just a matter of plugging and chugging. As we take a look at our products here, it's going to be 3 moles times negative 394 kilojoules per mole. Again, it's products here. Plus 4 moles times the Gibbs free energy change for the formation of water vapor, which is negative 229 kilojoules per mole. Subtract from that the sum of our Gibbs free energy change of our reactants, which is 1 mole times negative 24 kilojoules per mole, plus 5 times, oh my gosh, we aren't provided with a value for oxygen. For Gibbs free energy change, you have to recognize that that change is going to be 0 kilojoules per mole, not only for oxygen, but also for any element in its standard state in your equation. And so then it's just a matter of plugging that into your calculator to solve, and we should get a Gibbs free energy change of negative 2,074 kilojoules. Boom. And again, this negative implies that this reaction as written is thermodynamically favored.